Okay, notes for heating curve graph. What this shows, the heating curve graph is going to show the curve as we heat from solid through liquid up into gas. So what that says there is temperature versus time graph, heating a substance through its phases. What I've now labeled here is the sections where you have liquid and solid. They're here at this point. The whole system becomes liquid. At this point, the liquid starts becoming and turning into gas, and at this point, it is all gas. This is when we call boiling. This is usually when it's boiling, when we see that there's still liquid in there. However, you can definitely see the bubbles of gas coming out. What I've drawn down here now is the molecules. You can see that there's some solid here, but then also some of the molecules are starting going into the liquid phase. The reason why this temperature stays so flat is instead of all of the temperature going into movement of molecules, some of the temperature goes in to break up these intermolecular forces, or to break up the strength of these intermolecular forces, and so the energy is going into the molecule and it's being used by the molecule and not being turned into heat. And that's where you get that flat plateau there. What I just drew here, the molecules on this up curve here, this is when the entire system is liquid, so there's no more solid in there. At this point, all of the molecules are now in the liquid phase, and so any heat that is applied to this system will directly increase the heat of the system, because all of these liquid molecules are now being moved faster by that heat, causing them to move quickly, causing more collisions, causing the heat to increase. At this point here on this plateau, we have the liquid molecules down here, and we also have some escaping into gas. When you see boiling, fun no fact, if you're watching a pot of water boil, the bubbles look like they're coming from the bottom. Well, that's not air, that's water vapor being released from the bottom and going through the liquid and being released as a gas. So this would be a water vapor molecule, an H2O. A lot think it's air coming out. So this here, same thing that was going on in this plateau. The heat's going into the system, but that heat is being used to release the intermolecular forces of these molecules. And when that heat is used, that energy is used, that energy is enough to release it. Once we get to this point here, then all these water molecules will be going. But the reason why this does not go up in system temperature is all the heat that goes in is being used by these molecules to break bonds rather than to move. At this point here, now we are completely in the gas. We did not get to this in our study. This would be if all of the liquid boiled out of the beaker, and then we were taking the temperature of the gas above in a closed system. That would be here, but you can see the molecules. At this point, all of the molecules are in the gas phase, and any heat applied to them will just directly result in those gas molecules moving quicker, which would increase the temperature of the whole system. The next page are phase diagrams. I've already written down for you the relationship between temperature, pressure, and the three different phases. I'm going to go ahead and label the three sections in there. If that's too busy for you, I'm going to take it out in a second. But this whole area here is solid. If you're in this spot on the graph, you're at solid. If you're at this spot, you're at a liquid. And if you're in this spot under this full curve, you're at a gas. Okay, so the way you read this chart is you have pressure over here in atmospheres, and then temperature. These are two measurements that you need to read this chart. And basically, if you know your pressure and temperature, you can find yourself on the chart. If I know my pressure is 0.5 atmospheres, and I know my temperature is negative 15 degrees, I know I'm right here, which is the solid form. So I can say at 0.5 atmospheres and negative 15 degrees, I will be a solid. That's how I read this chart. One quick note, I wrote it up here. This is not water in this example. A lot of times we use water, but this is a phase diagram for just a random molecule. I just added 2 points. We have the boiling point or the boiling line, and that's this line here. Okay, and if we're going from left to right, as we gain temperature, we would go from liquid to gas, or as we reduce pressure, we'd go from liquid to gas. And so, given certain coordinates, that will tell you when you're boiling. This point right here is called the normal boiling point. And what that is, if you can see this pressure line, this pressure is at 1 atmosphere, which is standard atmosphere. So at 1 atmosphere, this temperature is known as the normal boiling point. So for this molecule, or this substance, at 1 atmosphere, the normal boiling point is 140 degrees Celsius. That is the normal boiling point that does not change. The boiling point can change, however, based on a change in pressure. Adding here in purple, we have the normal melting point, same as the normal boiling point. That's at 1 atmosphere. Then we also have the melting line. Okay, so if I went from solid and I changed the temperature, I'd become a liquid as I went across, and that would be my melting line as I cross this line here. I just added this point here. This is called the triple point right here. And that's essentially, at that pressure and temperature, your substance is teetering through all phases, solid, liquid, and gas. So at this point here, it's possible to have all 3 phases. It's good to note that the triple point does not change based on atmosphere and temperature. That triple point will stay. Okay, so at 0.5 atmospheres and 10 degrees Celsius, that's where you have your triple point. This line here, I've added these 2 words, sublimation and deposition. If I'm going from a solid right to a gas, we call that sublimation. And if I'm going from a gas back to a solid, that's deposition. So that happens across this line here. It's also important to note, for boiling, that indicates liquid to gas. This line, if we were reducing temperature or increasing pressure, this line could also be condensation when the gas goes to the liquid. And same for this line here. If I'm going from solid to liquid, it's melting, but if I'm going from liquid to solid, this is my freezing and my freezing point and freezing line. This are my note sheets. Again, I take time to make sure I have all these points labeled. I would also use this space below, or any space on the side, to write the definitions of the different points that we marked on here. It's good to know where the points are and how to find them and how to read this graph, but it's also important to know what they mean. So if you'd like, you can go back and listen and check in and write your own definitions for each one of those points.